Hello everyone, today we're talking about sequences and summation notation, section 10.1 in our book. So our first question has given us a sequence, and they would like us to find the first four terms and then jump all the way to the 100th term and find the 100th term in the sequence. So first we'll start off finding the first four terms. So this was the given sequence. Obviously a sub n, meaning what term we are currently on. So if we're looking for the first term, for instance, a sub 1, we'll plug a 1 in wherever we see an n, and that'll give us a sub 1, the first term. So that's where we're going to start. So a sub 1, and then in the rest of the sequence, I will plug a 1 in wherever I see an n. So we can see the first term is going to simplify to negative 1 squared times 1/2. And negative 1 squared is going to give us a positive 1 times 1/2, meaning our first term is 1/2 of that sequence. So I'll go ahead and continue on this process till I get the first four terms. So a sub 2, meaning the second term. Wherever I see an n, now I plug a 2 in. So I'm going to get negative 1 to the 2 plus 1. I'm going to plug a 2 in for n, so I get 2 over 2 plus 1. Simplify a little bit. Negative 1 cubed times, and then obviously 2 over 2 plus 1 is 2/3. Simplify a little bit further. Negative 1 cubed, that's going to give us a negative 1 back. And 2/3, giving us the second term being negative 2/3. So continuing on, I got to find two more terms. So a sub 3. Now I go ahead and I plug a 3 in wherever I see an n. So I get negative 1, 3 plus 1 over 3, 3 plus 1. So negative 1 to the 4th, I'm going to skip a couple steps because now we kind of see the pattern. Negative 1 to the 4th is going to give us a positive 1 times 3/4. So our third term, a sub 3, 3/4. And then my fourth term, again, plug in now 4 wherever I see an n. And skipping steps, again, negative 1 to the 5th. So every time negative 1 is going to be raised to an odd number, it's going to keep it negative 1. And 4/5. So we can see the fourth term is going to be negative 4/5. So that satisfies the first four terms. And then they also wanted us to do the 100th term. So we can also do the 100th term. No problem. We can jump all the way to the 100th term, a sub 100. And that just means I plug 100 in wherever I see an n. So negative 1 to the 100 plus 1. Plug 100 in for n. So 100 over 100 plus 1. Okay, and that means negative 1 to the 101. Well, that's an odd power. So it's going to stay negative 1 times 100 over 101. Which gives us negative 100 over 101 for the 100th term. So we have satisfied the original question. We found the first four terms, and then we jumped all the way to the 100th term of the sequence. Next question wants us just to find the first 5 terms. And the key word here is recursively defined sequence. So recursively defined just means it takes the term before in order to find the next term. So I'll show you what I mean as I go through this one. So they've told us the first term, a sub 1, right? We've learned that denotes the first term is 1. So I need to find the first 5 terms, so I got to find a sub 2. So to find a sub 2, wherever I see an n, just like in the first example, I'm going to plug in a 2. So that's 1 plus this is the subscript now, a sub 2 minus 1. So if I simplify this, I'll see that the second term, to find the second term, I take 1 over 1 plus a sub 1. So to find the second term, I do 1 over 1 plus the first term, the previous term. So I can substitute in the first term, and so now I get 1 over 1 plus 1, because a1 was equal to 1, so I substituted that 1 in instead of the first term, and I can see the second term is 1/2. Okay, so that's my second term. Now I'm going to go ahead and I'm going to do the third term. They want me to go all the way to the first 5 terms. So the third term is going to be 1 over 1 plus a sub 3 minus 1, right? Because now I'm looking for the third term, so I plug a 3 in wherever I see an n. That's going to be equal to 1 over 1 plus a sub 2, right? Because now 3 minus 1, now I'm using the second term in order to find the third term. And if I simplify 1 over 1 plus, well, a sub 2 was 1/2. So that's 1 over, well, 1 plus 1/2 is going to simplify to 4 halves, 5 halves. So, sorry, that should be 3 halves. Giving us 1 over 3 halves, simplifying to 2/3. Okay? So I can see the third term then, 2/3, after I subbed in the second term. That's what recursive means. It uses the previous term in order to find the next term. So again, a sub 4, 1 over 1 plus a sub 4 minus 1. So we should start to see this pattern, this being a sub 4 minus 1. 1 over 1 plus a sub 3. So 1 over 1 plus. Now I plug in 2/3, because 2/3 was my third term. And then that's going to be 1 over, and let's see, 3/3 plus 2/3 should be 5/3. So we get 3/5. That's my fourth term. And now to find my fifth term, a sub 5, I'm going to do the same process. 1 over 1 plus, now a sub 5 minus 1. Well, that's equal to 1 over 1 plus a sub 4, which is 1 over 1 plus. We just found a sub 4 to be 3/5. And if I kind of common denominator, that's going to be 5/5. So then we're going to get 1 over 8/5, which is 5/8 after you rationalize it. So you can see the process here of a recursive series. Okay, so this recursive sequence just means I take the previous term, plug it in, find the next term, and so on and so forth, and we can find whatever term they wanted us to find here. Okay, now they want us to find the first 6 partial sums. So in order to find the first 6 partial sums, those being S1 through S6, we need to know the first 6 terms of the sequence. So in order to find the first 6 partial sums, we have to know the first 6 terms. So, using what we learned in the previous 2 examples, I want to find all the way from a sub 1 all the way to a sub 6, and then we can talk about how to find the partial sums. So a sub 1 just means wherever I see an n, I plug a 1 in, so I get 1 over 2 raised to the first power, so a sub 1 is 1/2. And I'm going to find the first 6 terms. It doesn't specifically ask us for the first 6 terms, but in order to find the partial sums, I have to know the first 6 terms, and then I can find the first 6 partial sums. So a2, 1 over 2 squared, so 1/4. a3, 1 over 2 cubed, 1/8. Okay, we can see how this pattern is going. So hopefully we can see that the fourth term is just going to be this number, this denominator multiplied by 2, so 1/16. And then we can see the fifth term is 1/32, and you can go ahead and check it if you'd like. And the sixth term is 1/64. Okay, so those are my first 6 terms of this sequence. Right, I'm just plugging in a sub 1, first term, wherever I see an n, I plug a 1. So I found my first 6 terms. Now I can work on finding the first 6 partial sums. So, the first partial sum, it's called S1, that's just equal to A1. Right, I don't have anything to add up yet. All I have right now to find my first sum is just my first term. So, my first partial sum is just 1/2. There's nothing to add up yet because I've only got one term. So now I want to find the second partial sum. What that means is I want to take my first term, so we got to keep these vocab words separate here, right? These are our terms. This is a sum. So I want to take my first term and add it to my second term. That's not a 9, that is an A. Still doesn't look much like an A, but it's my second term added to my first term will give me my second partial sum. Okay, so I'm adding up these first 2 terms to get to the second partial sum. That's basically what we're doing. Whatever partial sum they're looking for, we have to add up that many terms of the sequence. So I take A1 was 1/2. I add that to A2 was 1/4. Okay, if I get a common denominator and add, I get 2. Okay, so we can see that our second term added up to 3/4. So I've gone ahead and I've done the next 3 through 6 partial sums. Right, so keeping in mind again, I'm just taking the first 3 terms to get my third partial sum. So I'm adding up the first 3 terms, finding common denominator, adding, getting 7/8. Again, the fourth partial sum. I'm taking A1 through A4, the first 4 terms. I'm adding those first 4 terms together to get the fourth partial sum. And then I've done the fifth and sixth partial sum for you. Right, and we can see the pattern. We're doubling the denominator. Numerator is 1 less than the denominator. Next, sigma notation. What sigma notation is doing is it is condensing, and let me make this a little bit bigger. It's condensing a big long series, right? So they only want us to go from 1 to 5. So they're condensing this big long series into this nice, neat notation. So what this sigma notation is really telling us is, okay, I want you to start by plugging 1 in for k, and then you're going to add up each subsequent term until you get to 5. So what this looks like is, if I plug a 1 in for k, I get 1 squared. Then I'm going to plug every number in for k in between 1 and 5. So 2 squared, 3 squared, 4 squared, 5 squared. Okay, so now I can go ahead and find the sum. 1 plus 4 plus 9 plus 16 plus 25. And that sum from k equals 1 all the way to k equals 5 gives us 55. Okay. So, obviously, sigma notation, nice, neat, easier to write than maybe a whole sum would be. Okay, and I have a second example for us to try. So now, instead of starting at 1, they want me to start j at 3 and only go from 3 to 5. So if I continue the same process, I plug 3 in for j. So 1/3 plus 1/4, I plug a 4 in, and then finally they only want me to go from 3 to 5, so I plug a 5 in, I find a common denominator, add these up, and I get 47/60. Okay, so that sigma notation, when I write it all out, find the sum just from j equals 3 to j equals 5, I get 47 over 60. Okay, now they want me to write the sum without using sigma notation. Okay, so I'm just going to take my terms from 0 to 4. I'm going to plug those in for my I, and I'm going to just write out the sum. I don't need to find the sum. They just want me to write the sum from when I equals 0 to when I equals 4. So I go ahead and plug 0 in every time I see an I. Okay, then I plug a 1 in every time I see an I. Then plug a 2 in every time I see an I. A 3 in every time I see an I. And then finally a 4 in every time I see an I, because I am just going from 0 to 4, where I equals 0 to where I equals 4. Okay, so 2 times 0 minus 1, negative 1, over 2 times 0 plus 1, 1. So I get a negative 1 for my first term. 2 times 1 minus 1 is 1. 2 times 1, 2 times 1 minus 1 is 1. 2 times 1 plus 1 is 3, so we get 1/3. 2 times 2 is 4, minus 1 is 3. 2 times 2 is 4, plus 1 is 5. And we continue the process. 2 times 3 is 6, minus 1 is 5. 2 times 2 is, that should be a 3. 2 times 3 is 6, plus 1 is 7. And then, again, I screwed up. This should be 2 times 4. So that gives me 2 times 4 is 8, minus 1 is 7, 9. So now I've written this sum out without using sigma notation. And finally, now I want to write the sum using sigma notation. So I'm going to take this big long series, and I'm going to condense it in using sigma notation. Okay, so we're going to write a sigma notation, obviously, and then typically they start with k, or they use n or j, one of those variables, but it doesn't matter what variable you use. So k, I think we can see here what the pattern is, right? K is starting at 1, and then I'm taking and I'm cubing whatever value is inputted for k. And my k is starting at 1, going to 7. So now I've written that series using sigma notation, much nice, neater, more condensed than writing the entire sum out. So same kind of thing happening here, right? We'll use a variable k, sure, it doesn't matter what variable. And now we can obviously see, okay, we are taking square root of whatever my value for k is, and I started at 3, went all the way to 77. Okay, so they haven't shown me every term in between 3 and 77, but they're insinuating that all of these terms are included in my sigma notation. So now if I wanted to, I could go ahead and find the sum all the way from radical 3 to radical 77, but the question is just asking us to write the series in sigma notation. Okay, so try the example problems that accompany this on the PowerPoint. Do your best, and we'll go over them at the beginning of class tomorrow.